tries to specialize. I mean, it has, so the multiple data values, they sort of translate between, well, not no relation, for real part, complex parameters. So one is we don't have that analog for and then there's also, I think there's just an issue where the way that these multiple data functions, the values, but the actual functions, there's a lot of analog. Maybe trying to use some of the time using natural.
I spent the whole day trying to find these things, just find the definitions. I mean, thank you for the references. These things, well, of course, this is hard in anything when you're trying to learn something from a different point of view, or, but still, it's.
The way that Francis writes about these things is that, if you read kind of a critical mass of his papers.
I understand, yeah.
You sort of get his ideas.
Alas, one doesn't tend to have a time to read. Okay, so last time I talked about, without, well, sort of defining, but with leaving out details, the automorphic Langlands group, LF, as a fiber product over Vey groups of this indexing set, which I more or less described, of the Vey group. So it has a Vey group as kind of a base, but then all of these fibers differ by these elements in the indexing set. And then what comes out, this is all conjectural, of course, highly conjectural, and I hope correct for the most part, but it may, there may be need adjustments that haven't gotten quite right. But in any case, what this thing and the Galois group, they all have local embeddings. And so you have LFB. They all would have local embeddings, I should say, because this is all subjunctive. This would, you have to say would when you when you don't know it exists. Don't want to call these V, maybe I'll call them V like this. Okay, so the local, when we talked about this last week, the local Langlands group is essentially the Vey group, except it's got a little monodromy SL2 in it in the p-adic case. And these then are going to map into up to conjugacy, LF, WF, and Galois group. This would be the Galois group of FV over FV, the Galois group of FV bar over FV. And so I talked a little bit loosely about what would be conjectured about this thing. It's meant to be something that would parameterize automorphic representations, global packets of automorphic representations. And I hope that that is more or less correct. In my opinion, the proof of it, I think it has to come from beyond endoscopy. This very elaborate comparison that I and others feel quite anxious to try to get their teeth into. Hello, Matthew. You already got your teeth into it, but beyond endoscopy, so it seems to me that is the way the proof of things like this are going to have to go. Okay, so the fourth thing would then be, question?
Is there some obvious intuition why you think that this path is easier than the other one of going via the standard trajectories and then here rather than you say that you think this is easier to go?
Not easier. Nothing's nothing's easier, but you can see parts. I mean, it seems to me you can see parts of that already happening. All right, so I mean, the people, I don't know, and I'm really speaking out of turn, but the people that do, I mean, Grothendieck's theory is just absolutely extraordinary. I don't think anything like it has ever been done before in human history of that scope. But it's discovering new things. But it doesn't seem like, if the history of it is anything to go by, it doesn't seem like it's perhaps the way to prove it. And furthermore, whereas automorphic representations do have all of these, they have these techniques of trace formula and beyond endoscopy, which are hard enough, but they do work. And I would suggest also that something of the sort is already taking place, and I don't know whether Sasha would agree with me, but in the work of Francis Brown, for example, where he's already talking about, he's discussing motives and modular motives and their periods and so on, but he's already working with automorphic representations. I mean, these modular motives, they're not, it's not something that, I mean, he's already implicitly sort of doing that, starting with trying to start with the automorphic representation. Just the modular motives, well, you've got modular forms, and so it doesn't look like a surprise to anybody that you would start with them, because everybody, they're so old. But it seems to me that also suggests that you got to work with the automorphic representations first, I think. Okay. Was there something else? Let's see. Okay, so this would be on the motivic. Galois group. So let me write that as G script F to perhaps distinguish it from LF. LF is like the Vey group with a Latin letter there, just a regular Latin script letter, is a locally compact group, and maybe I'll write that for an algebraic group. So this would be a conjectural complex, and so this is already a simplification, a complex pro-algebraic group, depending, we've got an F there. I didn't actually practice before I came here because I was stuck on something else, but there's two fields. There's the field F and there's the field Q. This is, we're talking about motives over F, and I'm not in a position to describe the difference between the field F here and the field Q, where you hope to define this, over which you hope to define this group. So there's two fields kicking around when you talk about motives, and I can perhaps prepare it for a later lecture, but In any case, this depends, pro-algebraic group, it's not really defined over the complex numbers in this context, but it is if you take an embedding, the F's a number field, if you take an embedding, of F into the complex numbers. And what is it? It is with embeddings. So it should, with local embeddings, as in the top row there, but maybe I'll just say it, we'll put it all into one diagram. With mappings, as over here, as to the left, namely, these are not embeddings, but these are mappings into GF, mappings into TF. So there's something new that comes up there, and into this is the Galois. This is still the Galois group over F in both of these rows. So it is a group, a complex group, where you might look a bit odd that we're embedding a locally or mapping, it's not an embedding, but mapping a locally compact group into a complex group, but we shouldn't be thinking of it's odd. We've been doing this for the last 2 or 3 months. We've been mapping the Weil group or the Galois group into the dual group. Dual group's a complex group. The Weil group, haven't really stressed that, but the Weil group and certainly the Galois group are locally compact groups. So we've been doing this all along. And so that's, this is just in that spirit. Now, we have to say something about what these things are. So I'll complete this sentence with mappings as to the left over there, whose representations are from this group into G, L, and C, parameterized motives. Motive, I guess, is by definition is a map, sort of almost by definition, is a map of the motivic Galois group, is a representation of the motivic Galois group. It's something attached to the general linear group. Langlands, incidentally, when he set this up in his Corvallis conference, he had a slightly less refined version of this LF. He had it, we remember what we put for the constituents of LF are these really fundamental little pieces of things that are attached to automorphic representations of a given simply connected group, which are sort of, they're stuffed into the group, the simply connected group G, where there's no other room. They're the ones that don't come from any smaller group. Langlands had it a little less refined. He took his analog of this as something that's in GLN. So his construction was parameterized by automorphic representations of GLN like this. And so it's a little less refined. But GLN is basically the home where these things are going to, especially for motives, are going to live. And now, what's this mapping? I won't say in anything really precise how you define this, but what it is, roughly speaking, this is a bunch of, these are a bunch of compact real forms of simply connected groups taken over the Vey group. So I guess you'd call them, what do you call those things? Torsors? No, they're not torsors. They're gerbs. Yeah, they're little gerbs. They're not. I guess some gerbs are a lot more serious than this, but this is a surjective mapping that doesn't split. It doesn't have a backwards arrow in general. And all it means is that it's because we took this to be simply connected, because we took the fiber here to be simply connected. And it may be that we want to include all automorphic representations, and automorphic representations that might only occur for the adjoint group. Oh, that's right. Yes, as this. Remember, this is KC here was a compact group, and it was so KC was a maximal compact subgroup, not of the dual group attached to the given automorphic representation pi, but rather the dual group, but rather the simply connected cover of that dual group. So we've done something a bit peculiar to insist that this be simply connected, and it means that the data that goes into it may only be attached to an adjoint, to an adjoint group. If I'm babbling here, if by insisting always, no matter what the automorphic representation pi here is, I'm sorry, this is a GC, and C is the data that comes from an automorphic representation. It's the family of conjugacy classes. But this automorphic representation may the dual group may not be adjoint. No, excuse me, the dual group may not be simply connected. If this is an adjoint group, the dual group is simply connected, but we're insisting that this group, the thing that comes into here, we're insisting that it be simply connected. So you have a problem finding where this data, for which group in the isogeny class of the given group here, this data applies. It'll apply to one of them, but not all of them necessarily, and that's what's responsible for this being a gerb. Normally, this is almost like the dual group, or the L group, GL, which is a semi-direct product of G hat with WF. And so you might say, well, why, that's a semi-direct product. Why isn't this a semi-direct product? Well, it's for this reason. It's just a technical matter to account for the fact that the data here may not apply to the group whose dual group, namely the thing that goes into here, this thing, whose dual group is simply connected. I don't know if that.
It's not LC that's simply connected, but the fibers of this, not the KCs are KCs.
Mm-hmm. They're the KCs, yeah. Everything's simply connected. All the fibers are simply connected, yeah, compact group.
All the fibers are KC essentially.
That's right. And so that's the right thing to do. I'm sure that's the right thing to do. But that has the effect of making this map rather than a semi-direct product of the dual group or the maximal compact subgroup of the dual group, rather than making it a semi-direct product of that with this, it's just a gerb, just an extension.
What's the payoff for introducing this complication into this definition as opposed to using maybe just GLN?
Oh, well, it's much less refined if you use GLN. It's simpler if you use GLN, but it would, you're talking only about automorphic representations of GLN. So you want all automorphic representations of any group. And
Really do have to make this into.
That's right. I mean, this is what it is. This is the structure. This is the structure that we hope will govern everything.
How do I see the setup that not all automorphic weighted codes?
Yes, I'm about to do that. Yes. Okay, so I got distracted. This is this thing here. This is a fiber product. So this just like this is a fiber product. This is a fiber product. I'll have to say what this is presently, but this is a fiber product of complexifications This is a fiber product of complexifications of those LC. Remember, LC, we sort of originally came from a complex group, basically like the dual group, but we went to the trouble of singling out its maximal compact subgroup, so we'd have a locally compact group. But now we have to go back to the complexifications of these groups LC, and this is a fiber product. This thing here is a fiber product of all complexifications of LC, or the complexification of all LC, except for, well, of only those LC of Hodge type. And what I mean by that is, i.e., for every representation R from LC, so now I'm trying to say which LCs, I mean, this is just the fiber of this is going to be a complexification of one of the LCs. This LC is a compact group that sits in a dual group, and it's sitting in the Vey group. So the fiber of this is going to be a complexification of one of these things that sits here, but it's going to have to be of Hodge type. That is to say, for every R mapping LC into GLNC, and for every V in S infinity, okay, remember we got these local embeddings here. We got the Archimedean places in particular, and we would insist that the restriction, okay, these are just built into the automorphic representation that got you this KC in the first place, namely this data here. This data doesn't include the ramified places, but we're taking all of these C, and we're expecting that they should give us all of the data. In some sense, they should characterize the remaining data. So that's, I mean, that's something that would have to work, or otherwise they have to be slightly adjusted. So the restriction of R to the subgroup C star. Okay, so the Vey group, the real Vey group the complex Weil group is just C star itself. I haven't talked about the Weil group very specifically. Got the local Weil group at an Archimedean place is as follows. The Weil group of a complex group is just C star. It's just the C star itself. The Weil group of the reals is actually an extension of C star, not of the reals, but an extension of C star that doesn't split. It's an extension of order 2. It's easy to write down, and I won't do it right now, but the Weil group of the reals is something that contains C star as a normal subgroup. So you take one of these things, and for an Archimedean place, you restrict this mapping to C star. This is something that's contained in the Weil group, and something that is then mapped into LC. By this map. And we ask that be a Hodge structure. The non-motivic automorphic forms are precisely those whose Archimedean parameter, whose Archimedean representations are not of Hodge type. They're like eigenvalues of the Laplace-Beltrami operator that have nothing to do with weight 0 or weight 1. So that is roughly how this group is defined. So you only take those elements up here, which are of Hodge type, and then you just take the embedding of this thing into this thing. But then I got to say what this is. This, I can't be putting the Weil group here. We've figured out how not to use a locally compact group there, but I can't be putting the Weil group here. This is a locally compact group. And so this is going to have to be an algebraic group. And what is it? It's this lovely group defined by Langlands in the same article, this Corvallis article, Langlands Tanyama group. So this is, my board's getting a bit disorganized. Can I rub this off? So no, okay, I'll put it over here. So this is Langlands Tanyama group. And which is from Corvallis. And I'm just going to use emotive words. It's kind of like the algebraic hull. Of the motivic part. Of the Weil group, the global Weil group. So the global Weil group, some representations of the global Weil group into GLNC will be motivic, and some of them won't. And very roughly speaking, what Langlands did was to take the Weil group and slice off all of the, this sounds silly because this is a group, it's not the representations, but he slices off all of the representations that are, slices off the pieces of the Weil group whose representations are not motivic, and he then blows the other ones up and makes an algebraic group out of them, a little bit like what's happening here. So this has a kernel, but the image of this in here that's not in the kernel gets blown up to be a piece of this group. And it's very difficult. I've never been really through the proof of it. It's defined simply as a cocycle. It's defined as a two cocycle, I guess. Well, I won't. I'll get it wrong, but I didn't think about this. But it's defined. Langlands writes down a two cocycle that defines this algebraic group. As Kumar pointed out, it's related to a simpler group called the Serre group. The Serre group's connected, right? Serre group is a connected complex group. And so so there's something that was already in existence that had been defined by Serre group, which is a connected pro-algebraic group. And this is an extension of that by the Galois group. And that's right, that's what it is. It's a two cocycle. So the Serre group is not terribly different. Is not too hard to understand. It's been around, as I say, it's been around for quite a long time. I guess it's in his book on L-adic representations, and so that's a connected pro-algebraic group over the complex numbers. That's very nice, and this is an extension of that. It's so you need a two cocycle. It's an extension of that. It's an extension of the Galois group. It's an extension of the Serre group by the Galois group, and it's given by a two cocycle with values in the Serre group. And Lang just pulls that out of the hat. All right, so that is what perhaps I can propose would be the automorphic Galois group. And let me just say, this would be a big generalization. It really is the general version of the Shimura-Tanyama-Wei conjecture. If it's correct, it's a big generalization of the Shimura-Tanyama-Wei conjecture for elliptic curves. Over Q. All right, so some elliptic curves were known to be modular, and they thought that all of them, it was conjectured that they all were. So that's a modular elliptic curve is something attached to an automorphic, to a modular form. And the deal was to prove that every elliptic curve was actually belonged to this seemingly rather restricted class of elliptic curves. How about a proof? Well, it's fatuous to really say what you would hope would be a proof, but it's like what I said before. We can hope that I would hope maybe without. So we could hope that a proof might eventually follow by building on the methods of beyond endoscopy. One would need more of that. These are the methods of beyond endoscopy that are directed, we hope, at a proof of functoriality. So let's say, suppose they do lead to a proof of functoriality. So this would be at the same, in concert or together with. So you'd be building on the methods that would lead to a proof. Same methods, but something more. You're going to need one, I think, would obviously need something more. And I would just say maybe very general analogs. Of the techniques, which were very remarkable and very new and original by Wiles and Taylor. The techniques in the proof of Shimura Tanyama Vei. So those are going to, those don't look at all like the techniques in beyond endoscopy, and they're going to, I could just, one would imagine they're going to have to be put together. What else was something I wanted to say, but I can't remember what it is. So, oh yes, I mean, the way, I mean, just my intuition, and I don't know, you guys perhaps have sometimes different intuitions. Everybody has their own intuition, but my intuition is that you're going to have to, these are so big, these conjectures, that they're going to have to use everything in the book. And in particular, I mean, the modular elliptic curves played a very important role. Obviously, they played a role because that's what you're trying to show that all elliptic curves are. But modular elliptic curves, just in their own right, played a big role, I think, in the techniques of Wiles and Taylor. Well, you're going to need something like that for if this is going to work. And the obvious thing you're going to use, even though it doesn't include all motives, would be Shimura varieties. The theory of Shimura varieties is very rich, and we still seem not to be, there seem to be lots of things we don't know yet about Shimura varieties. We don't know, it's I think, a rather limited collection of Shimura varieties where we can prove that the cohomology comes from automorphic representations. It looks large when people write it down. I guess symplectic, I didn't think about this either, but there's lots of work done on relating automorphic forms to the cohomology of Shimura varieties. Shimura varieties, of course, come with motives. They're the algebraic geometry, but the problem that people have been working on since Shimura, years and years, is to relate the cohomology of Shimura varieties to motives. But when you look at the list of Shimura varieties, say in Milne's book, he's got a list. Milne wrote a sort of an article about Shimura varieties, an expository article in the Fields Conference that took place in the Fields Summer School, I think, that it was in 2003. Milne gave 2 or 3 weeks of lectures of Shimura varieties. And anyway, in one of his chapters, maybe chapter 9, he's got a sort of a list of all Shimura varieties. And the ones that where we know about the reciprocity leave many of them out. So there's lots that needs to be done with that too. And you got to know that that's not good. We're going to have to know that cold if anything like this is going to work. Okay. Queries, questions?
So is it just exceptional groups that's the problem, or?
No. It's I don't think so. It's there's Shimura varieties. I think it's PEL Shimura varieties. They're sort of the main ones that traditionally have. I don't even know if it's all PEL varieties. But then there's a bunch of Shimura varieties. Do they call them abelian Shimura varieties that are whose whose moduli are abelian varieties. I think they call those abelian Shimura varieties. That's only some of them. There's so you know that a Shimura variety parameterizes elliptic curves, and a Shimura variety, I mean, it's a moduli. Sorry, let's.
EL types parameterize abelian varieties.
That's right. That's right.
In general, they parameterize Hodge structures, but maybe those Hodge structures aren't geometry.
Well, the way that's right. Langlands also wrote on that in his Corvallis article, and he had them parameterizing motives. So he had these other Shimura varieties parameterizing motives. And even that is not everything, as I understand it. There are motives, there are Shimura varieties whose Hodge structure, and maybe it shouldn't even be called a Hodge structure, has rational weights, I think. So does that sound familiar? Or
That sounds like well, maybe we've seen before, but like the first time they see this in the exponential Hodge structures, they have rational and irregular.
That's right. That's right. So you got to figure. I mean, I think I haven't checked it, but I think Shimura varieties. There are still a collection of Shimura varieties with rational Hodge weight, whose Hodge structures have rational weight. So just as the extreme case that Langlands was talking about, where the Shimura varieties are moduli spaces of motives with extra structure, that's something that's due to Deline, actually. But then there's more besides that. There's Shimura varieties with, I think, with rational Hodge structure, and I think, and what you say, I think is correct. I suspect they have to be parameterized by they have to be moduli space for exponential motives. Nobody's ever considered that, but you got to figure that that's probably what is needed. No?
Well, I'm puzzled by why you would expect fractional weights, because.
Well, I think that's part of. I mean, I didn't go through Milne's classification, but Langlands, when he talks about Shimura varieties being parameterized by motives, he has a condition on the Shimura variety, and I forget what he calls it, but it rules out fractional weights. But I think the axioms of a Shimura variety include spaces that have fractional Hodge structures with fractional weights. I think one would have to. I'd have to. So it's in chapter 9 of Milne's article. It's at the very end of chapter 9 in Milne's article for the summer school in 2003. There's a volume on it, and I think that and then there's a condition Langlands puts on Shimura varieties, even though they're very general, if they're a moduli space of motives, but Langlands has a condition on it that it does not include things that don't satisfy this condition.
Usually you're not taking covers of Shimura, you're actually taking Shimura.
I think so. I think the axioms, well, I'm not, so I could stand corrected, but I think the axioms of a Shimura variety include these. And well,
depends on the author you ask, but again, I think the point is that there's this very general class of Shimura varieties that parameterize just really crazy Hodge structures that you wouldn't expect to be
rational Hodge structures. I mean, not rational Hodge structures, but Hodge structures with rational weights. So yeah, okay. So I've got a couple of minutes. I'm going to talk for one more lecture on these things. Yes.
Are you still planning to, last time you said you did a conditional formula also for the exponential motivic?
No, I said I wasn't going to do that. I was going to try to say something about the mixed motivic Galois group. And that's, I think I'm maybe a little crazy to do that because I don't really understand it, but I will try to say something about that. So did you have a question or?
No, I'm just totally confused.
About But what Shimura varieties?
Yeah, why you get fractional weights? Because I certainly know there are Shimura varieties that you don't expect them to be modularized this particular variety. That's true. But they're all integral weight structures.
I can look, and maybe you could look. Langlands has a condition when he, in chapter 4, and where he talks about Shimura variety, he talks about Hodge structures, rational Hodge structures. He has a condition that even parameterize having moduli space, Shimura varieties being a moduli space of motives is not valid. So he's got a condition. He said these are only for Shimura, and I forget the term. These are only for Shimura varieties that blah 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 do not satisfy that satisfy this condition. And then I think that those extra ones are at the top of Milne's list. Fractional weight, but one could check that. One could check that. Anyway, it's nice that there's lots of interesting stuff to do. But clearly, one's going to have to. I mean, if one wants to do anything like this, you're going to have to understand all of these things cold. So I would like to give. I won't start it now, but I'd like to. So that was section 4. Okay, so let's just call this on the future. And this is really just this. If this works out, it's really just a beginning, because we need to answer. There's further, as Waleed said, there's further pressing questions that really need to be answered, and I'm going to review those. There's about 6 or 7 of them. All versions of reciprocity in one form or another, or most of them versions of reciprocity in one form or another, that would also have to be fit into this. And to me, it seems very exciting. I mean, I would like to be able to understand what they are. For example, where do you get exponential? This is about motives. Where do you get exponential motives? As Waleed said. What about mixed motives? Where do you get those? What about periods? We sort of started off with periods. So there's many other things that we could, that you guys, that's you youngsters are going to have to be dabbling. So we'll meet on Wednesday at the regular time. No. That's okay. Because then you'll feel bad if it turns out to be wrong. What if this turns out to be wrong? Then, so I don't want to. What were you going to say?
No, it's totally interesting.
It is. I just I'm